All right, now we're ready to start part 2 of our equilibrium unit, or the first PowerPoint that we're going to deal with. We're dealing with the equilibrium constant. Now, we've had a little bit of experience with this when we looked at our electrochemistry. We briefly talked about our constants. Now, our learning goal for today is, what is the equilibrium constant and how can we use it to determine the shift in equilibrium for a particular reaction? So we're always, again, looking forward to how can we actually apply this information. First thing we have to figure out is, what is a reaction at equilibrium, or what is our equilibrium constant going to look like? And we're going to utilize, in this case, a capital K. Now, the reason why I want to specify that we're dealing with a capital K here is because, remember, if you in our previous unit of kinetics, we had a lowercase k, which was the rate constant. Now we're going to be dealing with the capital K, which is our equilibrium constant. And there'll be various subscripts that we'll end up putting with it in order to distinguish which one we were talking about at that time. Now, a couple things about our equilibrium constant. These letters that we have in there, the J, K, L, M, these are going to be our coefficients that we're dealing with from the balanced equation. Of course, by now we should know that the square brackets let us know its concentration, and the actual letters are the chemical species that are a part of the reaction. Now, one part that I want to make sure you note, that the equilibrium constant is usually given without units, meaning it'll be a raw number. So we don't have to worry too much there, at least at this part, of any unit to use for it. Now, what are a couple things that we can conclude about the equilibrium expression? One, equilibrium expression for a reaction is the reciprocal of that written for the reverse reaction. So, if I'm drawing, or if you see this funny looking arrow, one going forward and the other one going back, we know that for the forward reaction, or what we're used to seeing, it will proceed from left to right. But if we were to write our equilibrium constant for the reverse reaction, it's just going to be the opposite, proceeding from right to left. This is going to be important as we continue to go through, so make sure you're paying attention to make that note. Now, when balanced equation for a reaction is multiplied by a factor of n, the equilibrium expression for the new reaction is raised to the nth power. Thus, the new equilibrium constant is just the original, or the beginning or forward reaction equilibrium constant raised to that power. So we still have the same changes, and it just wants to make sure that we know the transference of the information. And again, K values are given without units. Now, K always has the same given value at a temperature, regardless of the amounts of reactants that we're going to deal with. And this is very, very similar to what we dealt with in our last unit. The only thing that was able to change our rate constant was temperature. In our equilibrium unit, only thing that's still able to change that value is the change in temperature. Now, for a reaction at any temperature, there can be many different equilibrium positions, but there's only one value for K. So in other words, if I change up the concentration, it will change the equilibrium position, maybe shifting it one direction or the other, but the constant is going to remain the same. Now, what about if I involve pressures? Let me go back one slide there for a second, because you want to make note that when you see regular K by itself, you're dealing with concentrations, which is what we're used to. But if you should see next to it that little subscript P, that's telling you that now we're dealing with pressures, or usual partial pressures. That's what you actually see. So we're going to be dealing with atmospheres, and those things are coming right back out again. Now, let's look at an example. We have nitrogen gas plus hydrogen gas forming ammonia, still in a gaseous state. And we're going to see this process a lot, so just, get used to it. But as this reaction goes, we should be able to also determine the equilibrium based on the partial pressures of these three substances or these three species. If I was to write the Kp, or the equilibrium constant for the pressure, it looks exactly the same, or almost exactly the same, as it would for the concentrations. The difference is, instead of square brackets, now I have the rounded parentheses, but I'm still using my coefficients as I was before as the exponents, and I'm still dividing the products, the concentration of the products, the pressure of the products, by the pressures of the reactants. So, still seeing the same pattern over and over. Now, let's use an example. Equilibrium pressures at a certain temperature, and these are the actual pressures that are given to you in atmosphere. We're now going to take these and plug it into what we just looked at in the previous slide, into our formula. So Kp equals the pressure of ammonia, given to us as 2.9 times 10 to the negative 2 atmospheres, divided by these two values multiplied by each other. So going ahead to start plugging it in, Kp equals these values. After that, all it is plug it into your calculator and solve to get your final answer, which should be 3.9 times 10 to the 4th. Again, K not having values, you will just report it as a raw number. Now, what is the relationship between K and Kp? Because of the fact that Kp is dealing more with pressure and not necessarily concentration, we have to have a slight difference in the variable. Now, the first thing that we're going to come to is that difference in n, or the change in n. Whenever we see that delta sign again, it's a change in n, or the change. So we're going to look at the change in the sum of the coefficients, products minus the sum of coefficients of the gaseous reactants. Now, the temperature is very important. We're still dealing with temperature in Kelvin, and our R value, if you remember this from our gas laws unit last year, is going to be 06 liters times atmospheres divided by moles times Kelvin. Now, using that information for the previous value, we can then determine what the actual equilibrium constant would be based on the concentrations of these species. So once we plug in our information, 3.9 times 10 to the 4th equals K times our two constants, and we know that we're at 35 degrees Celsius, we come up with our final answer based on our concentrations. Now, some of these things I'll run through very quickly because they're actually fairly simple. Homogeneous equilibrium just means all things are in the same phase, either aqueous, gas, or solid. Heterogeneous just means that we now have more than one phase in this party. Now, the position of a heterogeneous equilibrium does not depend on the amount of pure solids or pure liquids that are present. So, if I have a situation where I am adding, we'll actually come back to that. Don't worry. We'll come back to that one and see if it makes a little bit more sense. But the equilibrium, here we go, is a good example. The equilibrium is not affected if I was to add more O2. It should still remain the same. Now, these are just some things to make note of and make a little side note, change them into possibly diagrams or something so you can draw your attention to it quicker. If I have a K value that is much greater than 1, and you'll see this, that just means that 9 times out of 10 we're going to have most of our products lying to the right, meaning most of our concentration will be to the right in our formation of products. This is going to be the opposite if we have a situation where it is much smaller. If the K value is much smaller, that means that the reaction may not have occurred as much or to a significant extent. We'll go through examples. Now we're back here to another concept check. want to keep checking to see how it is that you're actually doing with these. So make sure you're keeping up with what we're doing. Now, if the equilibrium lies to the right, the value of k is what, or what should we expect? Based on the information that we have, also if the equilibrium lies to the left, what value of k should we have, or what should we expect from the value of k? Take some time tonight, again, go through it. Let me know if you have any issues, and we'll try to get back through those tomorrow. Have a great evening.